Hi there, folks. Here we're looking at solving exponential equations using logarithms. And there are two properties of logarithms that we're going to use for this. And really, these say kind of the same thing. But it goes back to that idea that exponential functions and logarithms are inverses. And if things are inverses, they essentially cancel each other out. And that's kind of what happens here when we look at what these properties are saying. Right here, what I have is I have an exponential function plugged inside of a logarithm. See, here's a logarithm, and inside of that logarithm, I have an exponential function plugged in. And what happens is when the bases match up, when I have log base b and b raised to a power, the exponential function, the b raised to a power, and the logarithm, log base b, essentially just cancel each other out. And when that happens, I'm just left with the r, with the exponent, okay? Likewise, this other one is saying the same thing. I have b raised to a power and I have log base b. And what happens is log base b and b raised to a power cancel each other out, and I'm just left with what's inside the logarithm, okay? These are essentially just what inverses do when they interact with one another. They cancel each other out. If I have log base b and b raised to a power, they cancel each other out. If I have log base 2 and 2 raised to a power, they cancel each other out. If I have log base 5 and 5 raised to a power, they cancel each other out. And that's all these properties are saying. And really, from our perspective, we're really just going to use this one here during this lesson, okay? This guy is used for if you're solving logarithmic equations, you cancel it out with an exponential function. But today we're going to try to cancel out exponential functions, and we're going to use logarithms to do that. So here's a log base b canceling out a b raised to a power. That's what we're going to use in order to solve exponential functions here, okay? So here's how this works. For solving the exponential equations, we're going to isolate the exponential part of the function. And essentially, that still goes back to working backwards through order of operations. We undo addition and subtraction, then we undo multiplication and division, then we undo exponents and roots. So that's where we'll get to that idea of undoing the exponent or undoing the exponential part of the function using logarithms, and then continue to finish solving what's left over, okay? So we isolate the exponential part of the function, we use logarithms to undo the exponential function, and then we're going to solve what's left. For example, if I look at something like this guy, when I look at this thing, the exponential part of the function is just whatever's being raised to the power. In this case, it's 5 to the a. So 5 to the a is the exponential part. It's the thing that's being raised to the power. And that thing's already by itself. If I just kind of rewrite this, that's 5 to the a equals 121. And so the question really becomes, in terms of exponential functions and logarithms, is how do I undo 5 raised to a power? And the answer is I use a logarithm. Since this is an exponential function of 5 raised to a power, I use a logarithm to undo it. And if it's 5 raised to a power, I need log base 5 in order to cancel this thing out. So to cancel out a 5 raised to a power, I just need a log base 5. Okay? And what will happen is that property we just talked about will cause the logarithm and the exponential part to cancel out. But just like any equation we've ever solved ever, whatever I do to one side, I have to do to the other side. So if I did log base 5 of one side, I have to do log base 5 of the other side. And what happens is over here, the log base 5 and 5 raised to a power cancel out. They cancel out and just leave me with the exponent, which is a. All right, that's what this property we were just talking about is saying. Hey, the logarithm and the exponential part cancel out. I'm just left with the exponent. So on that side of the equation, I just get a. On the other side of the equation, well, that's a job for my calculator. I know how to plug that into the calculator. That's where I do my change of base formula. It's the natural log of 120 over the natural log of 5. So natural log of 120 divided by the natural log of 5. Okay, so that's how we plug it into the calculator. And that's why understanding how to plug these things into the calculator was important. Because, well, as we start to solve these things and use logarithms to solve exponential functions, well, of course I need to plug these into the calculator to get these values. So for this one, I got a 2.97. And again, it's approximate. It's a rounded off answer. There's no exact value that would give me 120 when I did 5 raised to the power, okay? But when you think about it, it makes sense because 5 to the third power is 125. So yeah, it's going to be a little bit less than 5 to the third. If I look at this one, same kind of thing. Once again, I'm going to rewrite it just to give myself a little bit of space. But if I have 6 raised to a power, in order to undo that, I need a logarithm. So 6 raised to the power, the thing that will cancel out an exponential function with a base of 6, is going to be a logarithm with a base of 6. So to undo 6 raised to a power, I'm going to do log base 6. And whatever I do to one side, I have to do to the other side. So log base 6 of each side. And once again, logarithms and exponential functions cancel each other out. So here's an exponential function of 6 to the x, and a logarithm of log base 6. Well, the log base 6 and the 6 to the power cancel out and just leave me with an x. Over on the other side of this thing, once again, that is a job for my calculator. That's my change of base formula. In order to plug log base 6 of 45.6 into the calculator, I do the natural log of 45.6 divided by the natural log of 6. And I get approximately a 2.13. Sorry, 13. 13, sorry. It was so long ago, I couldn't remember. Okay? But again, it makes sense when you think about it, because 6 to the second power is 36. 6 to the third power is 216, so I must have a value that's closer to 2 than I have to 3 in order to get a 45.6. So make sure you think about it in context. It should make sense. Okay? If I look at the next one, now I have a situation where the exponential part's not exactly by itself. And the other thing you should note here, in terms of, solving equations, we always work backwards sort of operations, but there's some invisible parentheses here. That w plus 3, that whole thing is the exponent, so that whole thing is in parentheses. And so if you think about working backwards sort of operations, I would undo addition and subtraction first. So I'm going to add the 2 to each side. Next, I would undo multiplication and division, which I don't have any of those values right now. So next, I would undo exponents and roots. Well, in terms of undoing the exponential part of the function, that falls into the same category as exponents. I just undo it a different way. I don't use exponents and roots because the base is the thing I want to cancel out. I have to use logarithms. And so here I want to undo 5 raised to a power. So I need to do log base 5 of each side. Okay, whatever I do to one side, I have to do the other side. And once again, what happens is 5 raised to a power and log base 5 cancel each other out, so I'm just left with the exponent. It just so happens that the exponent this time is a w plus 3. Okay? Over here, I don't even need to plug that into my calculator just yet. I'm going to leave it the way it is for now. I'm going to finish solving this thing and then just get all the calculator stuff done with all in one shot. So here to solve, I'm going to subtract the 3 from each side. And now let's go ahead and start punching into our calculator now that we're done solving for w. Okay? Just to kind of save this for all one string of characters so I don't have to keep plugging in different things. So here to do log base 5 at 19, that's the natural log of 19 divided by the natural log of 5. And then minus the 3. So I get a negative 1.17. And that's it. Again, I could easily plug that back in and check it, okay? If I look at the next one, once again, I work backwards sort of operations. I undo addition and subtraction. There's none of that. Now I undo multiplication, division, so I have to undo the times 3 by dividing by 3. And again, that 2x is technically in parentheses, which is why I don't touch it yet. Now I have the exponential part of this thing to deal with, so now I'm going to undo 4 raised to a power by doing log base 4. And again, whatever I do to one side, I have to do the other side. Log base 4 and the 4 cancel, so I'm left with the 2x. And again, this one I'm just going to leave the way it is until I'm ready to punch it all into the calculator. And I'm going to divide by 2. So I end up with x equals, well, now it's time to plug it into my calculator. So here I go. Log base 4 of 9, that's the natural log of 9, divided by the natural log of 4. And then I have to divide all that by a 2. Okay? But notice by waiting until the end, I don't have to repunch anything into my calculator. I can do it all in one string of characters. So I get a 0.79. Okay? If I look at the next one, again, I undo addition and subtraction first, so I'm going to subtract that 10 from each side. I'm going to undo that addition. Again, the x minus 4 is technically in parentheses, which is why I don't do anything with it yet. And now from here, to undo the exponential part, to undo 2 raised to a power, I do log base 2. Whatever I do to one side, I have to do to the other side. Log base 2 and 2 raised to a power cancel out, so I'm just left with the exponent. Over here, once again, I just leave it the way it is until I'm ready to get to the calculator. Now I add that 4 to each side. And now I go reaching for that calculator. Here we go. That's going to be the natural log of 72 divided by the natural log of 2. Now I'm going to add the 4 to that. So I get a 10.17. Okay. Look at the next one, same kind of thing. Now I have an exponent inside of an exponent. That's probably going to mess with my brain a little bit. But again, there's parentheses around this. So to undo 30 raised to a power, to undo that piece of this thing, to undo the exponential part, I have to use a logarithm. So to undo 30 raised to a power, I do log base 30 of each side. And again, log base 30 and 30 raised to a power cancel, so I'm just left with the exponent. The exponent just happens to be an x squared this time. And again, I'm not going to bother with punching this in yet until I'm ready. And now to solve this, I would actually take the square root of each side. And remember, when you take the square root of each side, you have to do plus or minus that answer. But here it is. Plug it into the calculator. I'm going to do the logarithm first, so natural log of 50. Throw some parentheses around that, divided by the natural log of 30. Some calculators are a little bit squirrely when it comes to the parentheses, so just make sure you have them. So that's the logarithm. Now I want to take the square root of that, so I'm going to hit the square root of the answer. So once again, I don't have to punch anything else in, okay? And so it gives me a 1.07. Okay? If I look at this one, it says you invest $5,000 in an account that pays 12% APR compounded monthly. How long will it take the account to double? And so now this is going back to our exponential growth and decay functions. And so when I look at this one, this is growth. I want the account to double. The amount is increasing. And this is going to be my standard model for growth. And so we kind of have to reach back a little bit. This is the y equals a times 1 plus r raised to the t. Okay? And so I start plugging in the values here. The initial amount is the 5,000. The rate, we have to be careful because the units don't match. I have a 12% APR compounded monthly. And so I have a yearly rate compounded monthly. That doesn't match. I need to change that to a monthly rate. And so if I look at this guy, 12% per year would be, well, divide by 12, that's 1%. Now that's per month. And that's what I want to use. Because this is compounded monthly, I have to convert all the units of time to months here. And so what I get here, that's a 0.01 raised to the t. And notice it says, how long? How long will this take? Meaning t is my variable. T is the unknown. So that's this guy. And I want to know when the amount, when this thing is going to equal, well, it says, when will this double? So in other words, I want to know when this is going to equal 10,000 because I started with 5,000. Okay, and so I'm doing the same kind of setup I did before, but now it's, instead of giving me all the pieces on one side of the equation, it might give me a variety of pieces here. Now I can solve for t. And so watch how this works. Let's do a little bit of simplifying, like we normally would. That's a 1.01 raised to the t. And so now if I think about this from the perspective of what we were just doing, I want to isolate the exponential part of the function. I undo addition and subtraction, which I don't have any of that here. Then I undo multiplication and division. Well, I have some multiplication right here. I'm going to divide by that 5,000. And so that gives me a 2 equals, over here I have 1.01 raised to the t. Well, now that's an exponential function. I have an exponential function. To undo that, I need a logarithm. And since this is 1.01 to the t, I have to undo it with log base 1.01. And whatever I do to one side, I once again do to the other side. And yeah, it's a little weird that we have a logarithm with a decimal in it, but that's okay. That's what base I had, and that's what base I need to cancel out. So that's the base that I need for my logarithm. Log base 1.01 and 1.01 raised to the t power, those cancel each other out. So I'm just left with t. I'm just left with time. This other half, this is once again a job for my calculator. Here we go. To punch that into the calculator, it's the natural log of 2 divided by the natural log of 1.01. And it gives me a 69.66. But be careful here. That is what kind of units? And, when we think about this, we had to make the units match. We had to convert everything to months. That's months. That might not be the best unit for this particular type of problem. We typically want to know these things kind of in years. That's a lot of months, and that doesn't really compute for us. So let's divide that by 12. Let's convert that. 5.8 years, that makes a little bit more sense. Okay? And a lot of times when you do questions like this, it might ask how many years. And so even though you have to do the whole problem in months, make sure you convert it. Make sure it's a unit that makes sense. Okay? If I take a look at something like this one, it says a zombie horde has an initial population of 112. After 3 days, it's grown to 3,242. And yeah, I'm using something silly like zombies here, but you could do this with anything, any kind of population that you want to measure. And this is what somebody in like the field of biology might do if they're studying a certain species and studying its growth patterns. They would measure the population, wait a certain amount of time, measure the population again. And what that's going to show them is how quickly this thing is growing. That's going to allow them to calculate the growth rate constant for this particular species. Okay? And notice here, this asks for the growth rate constant per hour, but it gave me the time in days. And so we still have that theme of always making sure the units match. If I want the growth rate per hour, well, then my time better be in hours. So right here, that's going to be 72 hours. And so now this is a continuous model because we're talking about a population growth. And so our continuous model was A of t equals A times e to the kt. And this one is growth this time. Okay? And so from here, I just start plugging in what I know. I know the initial population was 112. I know the time that I was looking for is 72. K is the thing I'm looking for. It says find the growth rate constant. So the question is, what is the population? What's the end population over that period of time? And the answer is, well, it's 3,242. And so it's giving me the initial population and the end population so that I can compare those and solve for the growth rate. Okay? And so once again, if I'm solving this thing, I would say, hey, let's divide each side. So undo addition, subtraction, then multiplication, division. So I'm going to undo this multiplication. So I divide each side by that 112. And I don't know if this is going to work out evenly. If it doesn't, I could just leave this as a big fraction. Okay? Yeah, it gives me a 28.94. I don't really like that. Okay? So maybe we could convert that. Let's write it as let's just leave it as a fraction for right now. 1621 over, what was that? 56. Because it doesn't matter. I'm about to punch this thing into my calculator anyway. Again, this is in parentheses, but now I have e raised to a power, so I need a logarithm of base e in order to cancel this out. Well, that's the natural logarithm. So to cancel out e raised to a power, I do log base e, which is the natural logarithm this time. Whatever I do to one side, I have to do to the other side. Okay? Here, log base e and e cancel out, so I'm just left with the 72. Over here, I literally have the natural log of 1621 over 56. And when you look at this thing, what's interesting about this particular example, all right, is I don't have any logarithms left Like I don't have to plug this in using two different logarithms, is what I'm saying. Because it's a natural logarithm, I already have that button on my calculator. It actually makes this problem easier than some of the previous ones, okay? It's not like when I did log of 1.01 of each side in the previous example, and then I had to do my change of base formula. This one, I just divide each side by the 72, and I don't need a change of base formula. Watch this. It's already written as the natural logarithm. So I literally just have to punch in natural log of that fraction, the 1621 over 56, and then divide all that by 72. And so I get 0.0467. And that was the growth rate per hour. And those units become really important because if I were to ask a follow-up question like this, like what's the population after 5 days? Now that I've measured that population for 3 days, I can now make predictions about what's going to happen in the future. I can use that growth rate constant to make predictions. And so what I do is I start this equation over. I say the initial population was 112. I've got E. I now have the growth rate constant, which was the 0.0467. And now the time that I'm looking at now is 5 days. But again, I did this per hour, so 5 days is going to be 120 hours. And now I can use that to find the population, the amount of the population after 5 days, after 120 hours. See, so I can use measuring the population to find the growth rate, and then I can use that growth rate to predict future values, okay? And so I can just plug this right into my calculator. This is a kind of like the problems we did previously. Again, put that in parentheses, 0.0467 times the 120. And I get about 30,409. Okay? And again, that was the zombie population after 5 days, okay? But this can be used with any kind of biological example. An endangered species, you measure the population, you measure it again a certain number of years later, and you see this decay rate or something like that. Now you can make predictions about future values, and it can help you try to offset those curves. And so for something like this, a radioactive isotope has a half-life of 17 years. In 1983, there are 1,200 grams of the isotope present. Find the decay rate constant per year. And so if we want to find a decay rate constant, again, this is a continuous decay problem, which looks like this. And so what happens is I can plug the initial amount in, which is the 1,200 grams. K is the thing I'm looking for, but the time that it gives me in years is 17. So it gives me 17 years, but the question is, if I want to solve for K, after 17 years, how much is left? Well, this is where that word half-life comes in. The half-life means that after 17 years, I'll have half the amount. So if I started with 1,200, after 17 years, this thing is going to equal 600, okay? And now, once again, I can find the decay rate of this thing. So I divide each side by the 1,200. So I get a 1/2 equals e to the negative 17k. And now, once again, I need to cancel out e raised to a power, so I need log base e, which is the natural logarithm. And whatever I do to one side, I have to do the other side. And once again, log base e and e cancel each other out. This guy cancels with this guy. And so here's what I'm left with. I'm left with the natural log of 1/2 equals a negative 17. And again, what's nice about this is I don't have to use a change of base formula for this particular example. I just have to divide each side by negative 17. The continuous growth model problems are actually easier in terms of what you have to plug into the calculator. I literally have to plug in natural log of 1/2 divided by a negative 17. So here we go, natural log of 1/2 or 0.5 divided by a negative 17, and it gives me a 0.04. I guess I could go one more. I'll go 0.8. There we go. I'll go a couple more decimals. And that's the other thing. You'll find that these are very sensitive. And if I only round to 1 decimal, I'm not going to get accurate results when I go to reuse this K value, okay? And that was per year. And see, that's important for this because it's a lot nicer to have a decay rate that's per year rather than the half-life that goes in 17-year increments, okay? And now I could easily use that to make predictions about future values.